Hello everyone. Today I'll be discussing my topic on integrated assessment models and its relevance to energy engineering. For the outline of the discussion, I'll give a brief introduction and then give you examples and types of integrated assessment models. How do these models work? I also give the future energy mix, emissions, and temperature based on the models, the strengths and limitations of integrated assessment models, and then finally the conclusions and future direction. First is the definition of integrated assessment models. It's a scientific modeling that integrates information from various disciplines, meaning it's interdisciplinary, and the fields include economics, energy system, agricultural system, land use system, climate, and so on. So compared to focusing on a single system, say for example, we just focus on the energy system and um, we model the energy system in such a way that we make energy cheap, then we would not know what is the impact on the land use, what is the impact on the agriculture and economy, and whatever we decide may have a negative consequence. Unlike in an interdisciplinary model, then we are considering all of these subsystems and we can know the impacts of these subsystems on each other. Integrated assessment models answer the questions what would happen if, or how could we get to. For example, as example question B, what if the world takes no action to limit climate change? Or what if countries impose a price of $100 per ton of carbon dioxide by 2020? What if certain technologies such as nuclear or carbon capture and storage are not available? And should we build a coal plant or a renewable plant today? So as you can see, these are important questions that we cannot answer on our own and we need integrated assessment models. Integrated assessment models were actually built for investigating climate impact. So as we all know, the impacts of climate change include falling crop yields, decreased water availability, sea level rise, ocean acidification, etc. So in response to that, in 2015, we had the Paris Agreement wherein we aim to limit global warming to well below 2 degrees Celsius and pursue efforts to limit it to 1.5 degrees Celsius. So the integrated assessment models were first used by the IPCC, or the Intergovernmental Panel on Climate Change, for climate studies and to run scenarios. But globally, it's not just, although that is the most popular use of integrated assessment models, it can also used for, say, for example, estimating economic impacts from future energy demands due to climate change, evolution of and future perspective of energy intensity. So energy intensity is the amount of energy per square meter of a building. So we can use IAMs to estimate that. The cost of CO2 transport and storage in global integrated assessment modeling. So um, we can also use integrated assessment models to calculate these things. And then for locally, I did not find many studies using integrated assessment models. I only found actually just one. which is investigating the watershed system using integrated assessment models, but the results were not published. However, we can use IAMS to say, for example, since the Philippines vowed to reduce emissions by 70% in 2030, then we can use it to estimate the economic impacts of our proposed policies to meet our pledge to the Paris Agreement. So in fact, integrated assessment models are like crystal balls. So we feed information, we feed data, variables, scenarios to the crystal balls, and it makes predictions according to our input. So for example, we want to know what if the, the question earlier, which is what if we don't do anything about climate change? Then it will show us, the crystal ball will show us the future of that scenario. So if we feed the crystal ball, what if um, we make sustainable decisions today, then it will show us the future for that scenario. So it's used to making predictions, making projections, calculating the impacts, tracing the effects of policies. So if for example, in the Philippines or globally, we have climate change mitigation policies, and we want to know its effect on the economy, on people, etc., then we can use IAMS, and then it's used also for estimating uncertainties. Since our course is on energy engineering, what is the relevance of IAMS in energy engineering? So there's strong scientific evidence that greenhouse gas emissions, human-made GHG emissions, are the cause of global warming. So energy engineering is, we are responsible for creating solutions and technologies that would ease out fossil fuels from the economy. Previously in this course, we discussed energy resources, conversion, storage, transmission, and distribution. And all of these things, they are inside the integrated assessment models, as you will see later. So, in fact, and energy engineering is very relevant to integrated assessment models because we have an energy model inside the integrated assessment model. How about the opposite? IAMS is also very relevant to energy engineering. So it's a two-way relevance direction. Why? Because IAMS will shape the future of energy mix. More or less, we will base our decision that would affect the future energy mix. We will base those decisions using integrated assessment models. So they are very relevant for to each other. Moving on to the types and examples of integrated assessment models. The first is, we only have two. So the first one is low resolution, which are simple IAMS models that we can do in spreadsheets. So they use simplified equations and they only consider two models inside. We have the climate and economic models. So the interaction between these two models, and that composes the low resolution IAMS. And these are examples of the IAMS models using which are low resolution, dice, rice, uh, ICAM, page, and fund. Don't worry about the meanings of each model. So it stands for, these are acronyms, but we'll not go into those details anymore because there are so many IAMS models. In contrast with the high resolution IAMS models, these includes details on the energy. So previously there's no energy, it's just climate and economy. But for high resolution, this contains energy, energy use, societal trends, land use, etc. And this is an example of that. As you can see, it's not just economy and climate. So we have land use, we have health, agriculture, economy, water, transport, other submodels. So it considers human and earth systems. So and examples are AIM, GCAM, image, etc. And this just shows a table of the different high resolution integrated assessment models that are being used by the Intergovernmental Panel for Climate Change, or IPCC. So they use these models to make their um, reports. We have a recent report this August, and they publish that every 6 to 7 years. So what is inside the reports? It's the status and updates on the global climate change. So maybe you're wondering, why are they using many models? Why not just one? And each model is being run by different institutions and different countries. So to increase our confidence with the results, we cannot just use one model. So we have to run the scenarios using different models so that if there are discrepancies, we can know why. What's the difference between these models that could explain the discrepancy? And as you can see later, the results from these models more or less agree with each other. They follow the same trend. So it increases our confidence on the results of our modeling. And how do they exactly work? As I mentioned, there are submodels inside the integrated assessment model. So it's like a model within a model. For example, for human systems, we have the energy model, population model, economy model, security model. For the natural earth systems, we have the atmospheric chemistry model, the ocean model, hydrology model, carbon cycle model, etc. And these submodels interact with each other, as you will see here. So, for example, this is our IAMs with the economy, energy, land, and climate submodels inside. So we input uh, the GDP, population, policies, and other assumptions. Say, for example, our scenario, and then these inputs enter the model, and inside um, there's interaction between the submodels. For example, the output of the economy will be used as the input of the energy system, but at the same time, the output of the energy system will be used as the input of the economy, and so on and so forth. So um, the input and output flows from one submodule to another, so that ultimately the results would include, say, economic outcomes, emissions, energy pathways, land use. And we might think that, well, these are very simple models and they're just flow charts, but in reality, these are all codes. These are in programming languages, and maybe that's why we have few experts in our country. So if you want to be an expert on this, I think we really need IAMS modelers in the country. Um, okay, so as I mentioned, there are many submodules in IAMS, but our focus is on the energy system because that's our course, energy engineering. But just to brush through the other modules, we have the MAGIC, which stands for Model for the Assessment of Greenhouse Gas Induced Climate Change. And inside that, we have the ocean carbon cycle, terrestrial carbon cycle, and climate. And then we have the agriculture and land use and other models that are other submodels not included here. But again, our focus is on the energy. So let's go to the energy model inside IAMS. So what can you notice about these things? We actually discuss these topics in our class. So that's why I'm saying that energy engineering is relevant to IAMS and vice versa. So we from energy demand to extraction to transformation and delivery. Um, the energy model inside the IAMS considers all those things. And just like the IAMS have different models, we also have different energy models. So let me clarify. These are not IAMS models. These are the different energy models that can be used inside the IAMS. So we have this. Don't worry about knowing everything. We'll not go into details, but they differ, for example, in the mathematical structure. Say some are optimization, some are market equilibrium, and then they differ in the scope. Some are national, some are regional, some are global. So IAMS can be applied globally or nationally or regionally, depends on the modeler. And each models also has their own forecasting period. For example, some would run until 21st century, some are just the mid-century. So they differ in the forecasting period. In the same way, IAMS would also differ. The different IAMS models would also differ in these aspects. Now let's go on to the different pathways or future scenarios. So as I have mentioned earlier, IAMS are like crystal balls wherein we input information so that it can predict the futures based, but we input a scenario, for example, like I mentioned, but if we don't do anything about climate change, so it always has to be, there always has to be a scenario that we want to check out or we want to predict the future on. So in order for the scientists to be on the same page, they named these standard scenarios. So they called it the SSPs, or social shared socio-economic pathways. And what my example earlier on, the question, what if we don't do anything about climate change, that's actually SSP5, fossil fuel development. So so that when the scientists, international scientific community, when they run a scenario, they know what each other is talking about, what scenario or um, what conditions, and um, they can compare the results side by side because they're using or they're talking about the same scenario. So the other scenarios are SSP1 is sustainable development, SSP2 is middle of the road, um, SSP3 is regional rivalry, and SSP4 is inequality. So for sustainability for SSP1, there's low challenge to mitigation. So in this scenario, we want to mitigate climate change and we do our very best. And then for the others, the level of the challenge to mitigating climate change varies. So I just want to show this future emissions and temperature based on the different scenarios. So in this figure, as you can see on the left, this is the emissions CO2, and then the on the x-axis would be the year until the 21st century. And like I mentioned, SSP5, which this is a scenario that we still dependent on fossil fuels, show that the global emissions of CO2 is still large. And then for the temperature increase, this is a temperature increase. So if we don't do anything and still rely on fossil fuels, then in the 21st century, the temperature increase would be 5 degrees Celsius from the baseline average or the pre-industrial average. Right now, we are just 1 degree higher than the pre-industrial average. But if we continue to rely on fossil fuels, then in the 21st century, maybe what age would be that time, but it would be our daughters and sons experiencing that. So it's 5 degrees as compared to the sustainable scenario, which has a lower CO2 emissions. It's projected that it's about 3 degrees higher, and it's more bearable than the 5 degree scenario. But that's not enough for the Paris Agreement. The Paris Agreement is 2 and then 1.5. How about the future energy mix? So this one is not based on the different scenarios. They're just running as the same scenario. I'm not sure if SSP1 or SP2. Anyway, it just compares the results of the different IAMS models. So as I've mentioned, as you can see here, even if we use different IAMS model, the trend is the same. If we want to mitigate climate change, we have to electrify. Okay, we have to convert to electrification. So using electric vehicles, for example. For the fossil fuels, it should decrease. So the trend is the same using the different IAMS models. And for the renewables, it should increase. So more or less, we are confident. We will be confident with our decision because the different IAMS models are showing the same trend. So this is another view on, but still about the future energy mix. It shows here the baseline scenario. What if we're not doing, what if we don't do anything? What will be the future energy mix in 2100 based on the different IAMS models? So here we can see that there's still a heavy reliance on coal and oil and gas. But if we try to limit the global warming to 2 degrees, then all of these fossil fuels decreased, and we are now more reliant on biomass and renewables and even nuclear. So that is what the different models are showing. Now let's go on to the strengths of IAMS. Well, the first is it's integral, so it is interdisciplinary. Hence, we know that what we're considering is not just the benefit of one field, say not just for the economy, but it's also for the climate and energy, etc. It considers the feedbacks between various domains. It has a broad perspective, okay, and it's global and considers long time scales up to the 21st century. So these are all the strengths of IMS, but of course there's still limitation. There's a trade-off between depth of coverage and breadth of coverage, meaning if we want a deep analysis, then the scope would narrow and vice versa. It's high complexity. This picture shows an example IMS. It's very complex. It requires high computer power and computer hardware also. And then uncertainty analysis is difficult. qualitative data is difficult to quantify. Say, how do you quantify political constraints? How do you quantify the consumer preferences? That's a very difficult thing to do. And then the future is uncertain. We can never know what will happen. Maybe there's an innovation that would give us cheap energy for a cheap cost. I mean, for a cheap technology. And then the limitation is the validity of our assumptions. How do we know that our assumptions are correct? In summary, so for this presentation, I gave you an overview and context of integrated assessment models. I mentioned global and local applications, the relevance to energy engineering, the types and examples, and how integrated assessment models work. I also showed you the future energy mix based on the different integrated assessment models reports, and I showed you the strengths and limitation of integrated assessment models. So integrated assessment models provide the much needed decision support in policy and decision making, but they do have their limitations. The future energy mix is based on the recent IAMs shown more reliance on renewables and electrification and less dependency on fossil fuels. So that's the direction that we're aiming for. And then IAMS has an important role in transforming the future of energy systems. That ends my presentation. Thank you very much, and I'm ready to answer your questions.